Hello everyone, this is Orhan. In this video, we will be talking about dimension reduction. In many datasets, the number of variables are so big that it prevents us from working efficiently. So that's why we have to reduce the number of variables. And there are many ways of reducing the number of variables. Looking at summary statistics, correlation, visualization, and principal component analysis are some of those. Let's start. As always, let's start creating a Python file in the folder where our data are. Let's click on New and create a Python file. And I'm going to name this as 4-dimension reduction. First of all, we must import necessary libraries. These are all the libraries that I'm going to import. Run it. Okay, and then I'm going to import the housing file that we used before. I'm going to call it housing.df. Okay, once you import the data, you might want to see the properties of the data. The first one might be to see the first couple of rows. So this is the command. So it shows us the first 5 rows. If you write here 6 or 10, you can change the number of rows that you might want to see. The other thing we might want to check is the descriptive statistics of the whole data set. The describe command gives us all the descriptive statistics of the variables in the whole data set. If you want to see the descriptive statistics of the variables individually, you need to write the code as follows. So first of all, you have to write the data frame's name. And then in square parentheses, you have to use the variable's name. For example, crime. This is the crime's name, the variable name. And then write the statistics you are interested, or write describe to see the descriptive statistics of the variable, of the crime variable individually. But instead of describe, you can write here mean, and then see the mean value of that variable. Also, you can construct a sentence, for example, as follows. And then comma, put what we have written before, and run the code. So first of all, it gives the sentence, and then it gives us the statistic. Of course, you can round the statistics. It rounds the number to 2 decimals. Another thing that we should also be checking when we are dealing with dimension reduction is if there is any missing value in the data set. So as you can see, none of the variables has any missing values in it. Okay, now let's also check the correlation that we have covered in the previous class. This shows the pairwise correlation between all 14 variables. Pairs of variables exhibiting strong positive or negative correlations often share a significant amount of redundant information, making them prime candidates for data reduction through the elimination of one of the variables. If you have difficulty in identifying which variables exhibit strong correlation in this matrix, it might be good to take a look at the heat map as follows. In a heat map, you can easily identify strong positive or negative correlations. Lighter colors exhibit strong positive correlation, for example, RAD and tax here. And very dark columns also exhibit very high negative correlations between DIS and NOx here. So basically, it does not mean that you should reduce these variables. It might give you an idea about what to take a look. The other thing is, correlation analysis serves as a valuable tool for identifying instances of variable duplication within a dataset. Occasionally, a single variable may unintentionally appear multiple times in the dataset, and correlation analysis can help uncover and rectify such redundancies. So redundancy can be identified by number 1. So if you see any correlation as 1 other than those in the diagonal, that might just tell you that those variables are the same variables. The diagonal ones show the correlation between the variables itself, so you can definitely ignore them. If you see any correlation 1 other than the diagonal, That might help you to take a look at the data duplication. Now let's take a look at another data reduction method, which is called principal component analysis. Let me say a few words before we start coding principal component analysis. Principal component analysis aims to reduce the number of variables. So this is performed by creating new variables through weighted linear combinations of existing ones. For instance, when considering a house's square footage, variables such as the number of bedrooms, bathrooms, and garage size might become redundant. We are going to remove the overlap of information between these redundant variables, and we are going to focus observations that vary the most along each dimension. And the final product is going to be a small number of numerical variables that contain most of the information. Basically, we are going to create variables that are going to be called principal components, and these components are going to be linear combination of the original variables. And few of these principal components contain most of the original information. So this method is an unsupervised learning. Basically, we are going to have features x1, x2, x3 until xp, and there is no response variable y. We are going to group these variables. Instead of p variables, we might have 1, 2, or 3 variables, which are linear combinations of all these p variables. We have px variables. We are going to create variable z. z1 might be a linear combination of all these px variables, and we might have z2, z3, or z4 until needed. One last thing to note before we switch to coding is there's a disadvantage of principal component analysis. Since these z's that I showed a moment ago are linear combinations of the original variable, it might be difficult to interpret new components because they correspond to the combination of original variables. I'm not going to review all the details, but if you are interested, you can take a look at these two books for the methodology and the theory. An Introduction to Statistical Learning with Applications in Python and Data Mining for Business Analytics might be good resources. Now let's take a look at Python coding. In this part of the class, I will be using cereals data which were collected on the nutritional information of 77 breakfast cereals. For each cereal, the data include 13 numerical variables, and we will be interested in reducing this dimension size. You can also use the same methodology to housing data, but this cereal data might be helpful for grasping the idea. Let's first start by importing the libraries. Now let's import the data, which is an Excel sheet called cereal. Okay, as I said, this is a data from this web page here. I just copied and pasted to Excel and then saved it as a serial data. Now we are importing it to Python. So these are the first 5 rows of the data sheet. And now let's see the descriptive statistics of the data. Serial df.describe. Run the code. So these are the descriptive statistics of the data. As you can see, there are 77 rows, which means there are 77 brands. Now I will be showing you 2 examples, one with 2 variables and another one with 12 variables. In the first example, I will be picking 2 variables out of our data set, and I will be reducing it to 1 only, which is the only possibility. Okay, so which variable will I be choosing? Well, to do that, I will first be looking at the correlation table. So this is our correlation table. As you can see here, there are a couple of light colors here which shows high correlation. I will be picking calories and sugar, so which has a correlation of 0.6. So what I will do is I will create a new variable which is going to be called principal component, and this is going to be a linear combination of both variables. Let me do that. Okay, when we run the code, we see that the computer created one principal component only. Now let's take a look at the performance of that principal component. To do that, I will be writing another code. Okay, this code tells us three things, but the most important one is the second one. The second one, which says proportion of variance here, is showing us that our new variable, which is the first principal component, explains 78% of the variation which is created by calories and sugar together. So instead of using calories and sugar, if I use PC1, which is principal component, I will basically be covering 78% of the information which is explained by calories and sugar together. So instead of performing a prediction based on the whole data, which is 2 in this case, we can only use this one new variable. That's the idea of a principal component. If you want to see the entries of this principal component, we should write the following code. This code gave us the numerical values of principal component. I sometimes say first principal component, which might not make too much sense here because we have only one principal component. But in the second example, I will be showing you an example with 12 variables, and in that case, we might have more than one principal component, and in that case, that will make more sense. Okay, now let's take a look at an example with more variables. Now here I will be taking all of the variables from my data set and I will be reducing them to 3 variables only. To do this, I will be copying this code from here and then changing a couple of things. So first of all, this is going to be PCA2, just not to confuse the computer. So this is a new analysis. And number of components is going to be 3. This is PCA2 again. And instead of taking calories and sugar, I will mainly be taking all of the columns except the first 3 columns, because in the first 3 columns there are categorical variables which I will not be using. This is the first column, second column, and third column. They are all categorical variables. I will be adding a tiny little code here just to tell Python to drop the first 3 columns. Okay, so the code is working. So there will be 3 principal components. Now I will be measuring the performance of these 3 components. Again, to do this, I will be copying the second code from here, making tiny little changes here. So this is going to be PCA2, second analysis, PCA2 again, PCA2. There will be 3 columns, PC2 and PC principal component 3. And if we run the code, so we see 3 principal components. As you can see, the first principal component explains approximately 25% of the variation of all 12 variables, second one 18%, and third one 15%. So these 3 variables explain almost 60% of all the variation that are explained by the original 12 variables. In other words, instead of using 12 variables, if you use only these 3 variables, you would be explaining almost 60% of the whole variation that are explained by the whole data set. If you believe 58% or almost 60% is not enough, you can increase number of principal components to 5 by changing this n to 5 and run the code. And then you should rerun this second part, but you should add 2 columns here, 4th principal component and 5th principal component. Right now you added 20% more explanatory power, which makes the total 78%. In other words, these 5 principal components are explaining 78% of the variation in the whole data set. You might also want to see how our original variables contribute these 5 variables. To do this, we will write the following code. These are basically the coefficients of every single original variables. So for example, first row shows how these 12 variables contribute to first principal component. That these are their coefficients. This is second principal, how they contribute to second principal component, etc. If you want to see the entries of the principal components, you can write the following code. These are the first 5 rows of our principal components. Again, unfortunately, it's very difficult to interpret the principal components, but the following heat map might help us understand what's going on. So I will be writing a code to show you the heat map of how each variable contribute to the principal components. Okay, so on the y-axis, you see the principal components. On the x-axis, you see our original 12 variables. So, and then the heat map is showing the correlation of each variables with the principal component. So the lighter the color, the higher the correlation. For example, look at the fifth principal component, which has 4 here. Calories, protein, fat, sodium are highly correlated with this one. And first principal component are less correlated with calories, but for example, more correlated with fiber and potassium, etc. One plausible question is how many number of principal components is okay or is enough? I will answer this question by drawing a chart, and this chart shows us proportional variance explained with respect to number of components. So let me draw the chart and I will explain what's going on here. Now I will draw the chart. Okay, this chart is basically showing us what I showed you before here, how much percentage first principle, second principle, third and fourth and fifth principle components explain. This is basically showing that chart. So first principle component explains almost 28% and then 18% and all the way down. And the right chart shows the cumulative performance. So if you use only first principle component, you will have 25% only, and then goes up to 40 something, 60, 70, and almost 80%. So if you use 5 variables, you will more or less explain 80% of the all variation of all original variables combined. So in other words, instead of performing a prediction based on the whole data set of 12 variables, we can only use these 5 variables to increase efficiency. Coming back to our original question, the first variable explained 25%, second variable explained 18%, third 15%, fourth 12%, fifth 8%, etc. After some point, this cumulative distribution chart to the right flattens. Every single variable you add, do not add much to the explanatory power. At that point, you should stop adding new variables. There is no definite answer to that question, but in this question, for example, 5 variables explaining 80% is pretty much more efficient than using 12 variables. But in each question, the answer would depend on your evaluation. That's all about this lesson and principal component analysis. I hope you enjoyed the class. See you in the next video.